let's move on to the next one. Otherwise, you guys don't have time for lunch. All right. So design patterns, right? So like I said, we applied those design patterns to the system, and I will try to show you as much we can within time. Okay. All right. Sidecar. So one service is written in C#, but there is a cross-cutting concerns like monitoring or proxy going to remote service. Those are kind of common features across all services, right? So you may want to make this as a library running inside of this service. But the problem is there's another service here written in Python. And same concerns, monitoring and proxy. But those are different languages. How can we have a common libraries that can be used across those two services, right? One for C#, another for Python. So the Sidecar design patterns enables it by attaching those helper functions as a Sidecar container and enables the communication between primary app and helper functions through language neutral way like HTTP REST or shared file, right? And you can deploy those helper functions as a Sidecar containers by putting everything into a same pod. This is supported by most of the container orchestrator. Okay, I'll just pick up the pace, go faster. So if you guys have any questions, let's please ask me. An ambassador is special form of Sidecar. So service A calls service B. But it's not that simple, right? When you call service B, you have to think about those things. Something bad happens. You have to retry that operation, or something keeps failing. You may have to circuit break that calls. Or service A may be able to call B, but not C. How can you manage those authentication? And most likely, service B is running as more than one instances, and you have to load balance the request going to the multiple instances, or routing, or tracing. How can we do this, right? This is very common in any inter-service communications. Ambassador pattern is to have a proxy that takes care of those things. And when you use a service mesh, like this is the example of Istio, one of the service mesh technologies. Envoy is a proxy, takes care of those things. So instead of you do these things, right? Envoy comes with Istio, the service mesh, does these features for you. So you don't need to do anything. You have to configure those things, but the Envoy does it for you. And Envoy is the ambassador running as a Sidecar. Okay? Oh, stop working. Something happens. All right. Okay, so retry. So one operation fails. You have to retry that operation. That could be done by the ambassador. But if it keeps failing, do you want to still retry? Maybe not, because you're just wasting your time and also wasting your resources. While you keep retrying, you are holding the resources like threads, memory, or network connections. Until you give up that operation, you are holding the resources, right? So instead of keep retrying, you can circuit break. It works exactly same as a electrical circuit breaker. So when you open that breaker, no request calls are going through that breaker to that remote service. And instead, this guy just give it up, right? You guys, this guy keeps failing. So I will give it up for next 10 minutes, then return to the client saying, oh, it failed, without even attempting to call that guy, because we already know that this guy will fail. Right? That's what circuit breaker does. And this is more like a little more in depth, right? So this pattern manages those three states: closed, open, and half open. Closed is the normal state. Every request are going through. And once any number of failures are happening in m minutes, like for instance, 100 times failure within last 3 minutes, whatever you configure. When it goes beyond that threshold, it trips to the open state where no calls are going through. You shut it out, then return to the caller client saying, oh, all of your requests are failing. But in this state, you are kind of checking the remote service by letting some percentage of the requests going through. Let's say 10%, right? 100 requests coming through, only 10 goes through to that service just for checking. And if those 10 requests succeeds, you can now think that, oh, this guy may be recovering from the failure, right? Then let's go back to the closed state and let all the requests go through that service. That's how the circuit breaker works. The good news is you don't need to do this. Like what I said, the service mesh does it for you. But even without service mesh, there are a couple of components, a few components like Poly for the .NET, Hystrix for Java. Using those libraries, it can does this for you. It will do this for you. Scheduler-agent-Supervisor. This will kind of answer to the question from that gentleman. So scheduler takes care of a workflow. This is very common, right? In microservices, no single services exist alone. You have to work with other services to complete the transaction, right? In this case, scheduler calls these three backend services: package, drone, and delivery. But the problem is, what happens if some of those operations fails, right? How can you make sure that the system is consistent? That's where supervisor comes in. So scheduler takes care of happy paths, right? Just keep dispatching requests to three services. Hey, here's a request, go your stuff. And something bad happens. Then this guy will check that if any failures happens, this guy will do some recovery process. It's app specific. So this pattern is agnostic to any type of recovery process, but those are kind of a responsibility of each component. Scheduler takes care of happy paths. This guy takes care of partial failures. In our examples, this is how it works. Like scheduler, takes care of happy paths. Everything works fine. No need for do anything. But in the case of those partial failure, step 1, 2 succeeds and 3 fails. What should we do? We used to be using. Then what should we do, right? So in our examples, the scheduler detects that the step 3 fails, then create a message that, hey, 1, 2 succeed, but 3 fails. Go fix it by putting that message into the queue to notify supervisor, hey, something bad happens. It's your turn to fix it, right? How can we fix it? So we used to be doing these things, like a question coming from that gentleman, using DTC for strong consistency, right? We lock all resources until everything succeeds or fails, right? So if something bad happens, we roll back all database. So there's all or nothing transaction. And it's very strong, consistent, and safe. It works fine, but the reason why we are switching from this model to the other is scalability and availability. Because now we are locking these resources until the transaction completes. And while we are locking resources, nobody else can access the same resource, right? Which is not good for scalability. So instead of doing this, what we do is here. So again, step 1, 2 succeeds and 3 fails. And this guy detects and notifies supervisor, hey, 3 fails. And what we do is, instead of strong consistency, the supervisor will cancel the succeeded operation. So in this example, package was already created and drone is already allocated. But this guy fails, right? So we need to cancel the request already happened to this service. Hey, I know you already created this package with this ID, XYZ, cancel it. I know you already allocated drone for delivery ID XYZ, cancel it. Instead of maintaining the consistency at the database level, we make the system consistent without making database consistent. This is how compensating transaction works. This is what we call eventual consistency. So at some point, it's inconsistent, right? Package is there, drone was there, but nothing's here. It's inconsistent. But by going through this cancel operation, then those guys will come back to consistent state. Makes sense? Good question. So cancel operation needs to be, consistent. So if by doing this and the cancel operation fails, then what we do usually is to ask some manual step. It cannot be automated, right? So asking those guys fails, cancel fails, nothing can be automated. So hey, with this request, something bad happens. So probably another queue, dead letter queue, a poison message saying, hey, this request has something bad in it. And notify administrators, hey, go fix it. Oh, right. So if it takes too long to cancel, right, drone will start flying to pick up that goods. It's just waste of the resources, right? So it has to be automated. We will retry these failed operations maybe 5 seconds, 10 seconds before canceling it. But if it takes too long before cancel it, those risks, we will see those risks. So you need to design those timings, right? Gentleman back over there. Questions? Oh, I see. So this database crashes, but this guy's he keeps running. How make it consistent, right? First you have to make everything redundant, right? So like it cannot be like one database goes down, then you lose that data. So by making every database redundant, you wouldn't see that kind of a partial, one database is not available versus the other. But there is some possibility that, one of those databases goes down, then in that case, you have to stop that operation, then, restore from the backup data, then start the business again, like in worst case. But you have to make enough redundancy, for those data so that. Yep. Mm-hmm. Exactly. So as many replicas you want, right, to prevent that from happening. But the chance is never be zero, right? So if that. Yep. The more service, the more chance to fail. Exactly. So in worst case, you have to stop the operation. But this is critical, right? So which leads to SLA, like uptime requirements. Like for critical business use case, you may require 3.9, 4.9 uptime. To achieve 4.9 uptime, you have to have a bunch of replica running for each of services and database. But it's still 4.9, not 100, right? So, oh, right. So it's all asynchronous. Yeah, that's fine. So actually, we have 5 services and 5 calls going to 5 services, all asynchronous except for the final one, because delivery service requires all the information, right? So first 4 calls: packaging, create package, allocate drones, and check the user account, and ask for the third-party, transportations. Those 4 service calls are done asynchronously. And once all those 4 calls are done, then this guy will call delivery service. Hey, here's the necessary information for you to manage the delivery. That's how it works. In our architecture, that's the responsibility of this guy. This guy keeps track of status of each request going into 5 services. And then, if everything works fine, we don't have this process, right? It's just done. But if something fails, then it will detect that failure, then create a message and put it into queue. Then let this guy to recover from it. Finally, yes. So this is all automated, right? But manual intervention is required for poison message, meaning like if this request causes too many failures, any number of retry all fails, to cancel that request fails. So something must be wrong with that message. That's what we call poison message, right? So those poison message will be put into dead letter queue, not this one. This one is the automated recovery. And it's not in this picture, but there should be another dead letter queue here, right? To put a poison message in it. Then for that poison message, we need to process it manually. Oh, that's a good point. So I kind of simplified the story, but supervisor doesn't, right? So this guy does. The supervisor will ask scheduler to cancel the succeeded operation. So this guy knows all workflow logic, but this guy doesn't. But it's kind of app specific, right? But in general, that's how this pattern works. Yeah, exactly. But also each operation running in this service needs to be idempotent, meaning like calling the same request with same ID, it wouldn't affect any. So these guys will dedupe, right? Detect the duplication and ignore a duplicated request. That's one option, right? So let everybody retry. And, only the guy who failed will do it again. That's one option. But what we are doing here is to retry only the failed operation because we track the status here. And finally, if all the retry going to this guy fails, then we cancel only the succeeded operation. That's one option. I'm not saying that's the only option, right? Like you pointed out, you can even simplify this. Retry all operations, then let them dedupe, right? That's another option, right? Or cancel all operations. And since this guy doesn't have any succeeded operation, they ignore the cancel request, right? To simplify things. But those are the kind of options. This is not the only one. Any other questions? Okay. Oh, I have 10 minutes. So, okay, event sourcing. Drone service keep sending events, right? Like a drone was scheduled, package was picked up, the delivery is on route, and also completed. Those domain level events are coming from drones to the delivery service. And usually what we do is to update the same data record, like drone was scheduled, picked up, on route, and completed. But the potential problem of this approach is that you lose history. When drone was scheduled, because we keep updating it, right? You lose that history. If it's okay, no problem, you can keep doing this. But if you want to maintain that history, there is another pattern, event sourcing. Instead of updating the same record, you keep adding a new record to that database. You append the record, append only, no update, right? So those 4 records. Now you can go back to see, hey, when package was picked up, you can pinpoint this record and see when it happened, right? But the sorry. Issue of this approach is now we lost the idea of current state. Which is the latest one? You need to replay all the events to see the latest. Oh, it's not working. Okay. You replay all the events from scratch to see, what is the latest status, right? So it's kind of trade-off. If this is maintaining a history is more important than getting the current status, this pattern works fine. Well, other way around, right? The materialized view. This is what we do in history service. Delivery service keeps firing event to a delivery history service. We are using event hub capture. This is kind of a very handy feature to store every event coming through event hub and then store those events into data lake or Azure storage. You don't need to write the code, any single code. You can just turn on the capture, and it does it for you. Right? It's very handy, but there is another use case, which is status inquiry. Hey, I ordered this request. What is the current status? And we were trying to, query against the data lake, but this is not designed for random query, this type of use case, right? This is designed for analysis or archive. So instead of letting data lake do everything, now we have another store, Cosmos database, to save the subset of the events just the required information for status inquiry use case. So only timestamp and the event, right? Timestamp and the status, instead of saving everything here. This guy has all the details about delivery history versus this guy has only timestamp and status to answer the status inquiry request. This is the materialized view. This is what we call materialized view. Bulkhead. In microservices or containerized applications, this is very common to share one node with more than one service, right? In this case, package, drone, and delivery. Those three guys are shared. They share the same node. Means share the same resources: memory, CPU, disk, and network, or something else. And what if package service start dominating, consuming lots of resources? The other two guys cannot work, right? So Bulkhead pattern is to configure the resource cap for each service. So in this case, here, the drone service requires those memory usage, and also you can configure the limits. But this guy cannot go beyond this limit. If he try to use more than those amounts, the request fails, right? So that any one of those guys cannot dominate the resource consumption. That's the Bulkhead pattern. But it works fine for this type of resources using containers. But if you want to do the same for thread pools, database connections, the container doesn't support it at this moment, right? So you have to do it yourself. But for this type of resources running on containers, it's very easy to do by just configure the resource limits. Load leveling. Let's make this as a final pattern. Load leveling. So here's the potential issue. You may see the spike of load coming, right? So let's say 100K requests per second. This is what we are dealing with, right? 100K requests per second coming. And if you do nothing, this spike is going into the cluster. And then eventually overwhelm one of the backend storages or services, because we are not designed everything for 100K requests per second, right? We are not designed for the peak load. 100K as a peak load, but we design, provision those resources for constant load, which is 10K. So if doing nothing, the spike will overwhelm your backend. And what load leveling pattern does is to have some sort of queuing mechanism in between. And in our example, we are using IoT Hub React as a consumer of the message coming through Event Hub to reduce the pace of processing down to 10K, so that every request coming inside a cluster will be reduced down to 10K instead of 100K. So the resources we provision for each service and data is for 10K, not 100K. Okay, this is how load leveling works, but it may more difficult than it looks, because just using queue is not enough. If you put message into the queue as fast as you can and get the message out of the queue as fast as you can, you don't reduce the pace, right? 100K going in, 100K going out. There's no load leveling. You have to control the pace of processing somehow. And we are doing it at IoT Hub React. This guy controls the pace of the queue from Event Hub based on the pace of processing at the backend. So the process slows down at this point. The process pace of the queue will slow down together. That's how IoT Hub React works. So this guy is perfect, works perfect as a load leveling. All right. One more pattern? Okay, so yeah, that makes sense. So this is the last one, right? So that was a load leveling, but this is kind of simpler. So instead of reduce the pace of processing, you can just reject the request. You don't accept the request, right? So again, 100K spike coming. Hey, I designed my system for 10K, not 100K. So simply, I don't accept your request. But this one may look simpler, but not easy to implement because you have to monitor the pace of a request coming, right? And it might be easier for single tenant, but if your app is multi-tenant, you have to monitor per tenant, and you have to reject the tenant making too much requests, not everybody else, not anybody else. So, yeah, exactly. Exactly. Like if you are dealing with different user SKU, standard versus premium, standard has lower threshold than premium, right? So you have to distinguish those user SKU. So it's not super easy, but maybe simpler than load leveling. All right. This is the last pattern. I have a couple more, but I don't want to crush your lunchtime. So any question before going lunch?